Hello everybody, welcome to my video. Today we're gonna be doing here's the title, the design of precast concrete reinforcement for crack portion of the beam. Okay, that's the title of our video today. The beam is right here, the precast concrete beam, and the beam is designed to sustain a shear load, a reaction load of 125 kips applied to the steel angle. The lower corner of the beam is provided an angle of the size 3 inches by 3 inches by 3/8 inches thick. The precast concrete beam is prefabricated outside of the site, so therefore during the transportation and installation of the beam, the precast concrete beam, it is possible that it will sustain possible cracking in two scenarios. Number one scenario is right here. The crack is analyzed from the edge of the beam running diagonal up to the bottom of the beam. The length of the crack, the horizontal length of the crack in the bottom of the beam is analyzed to be 4 inches, and also the angle of the crack is analyzed as 20 degrees. To prevent for the beam from cracking, we need to provide reinforcement running across, crossing the diagonal crack of the beam. This reinforcement is AVF. This is the total area of the reinforcement steel bar that we're gonna be designing. By theory, the reinforcement should be placed 15 in an angle of 15 degrees from the bottom surface of the beam. So it's 15 degrees angle like this, crossing the possible analyzed crack. The development length of the reinforcement, I extended I made it longer. I extended the development length up to 24 inches. The actual calculation of, by theory, calculation of the development length of the reinforcement is, the actual calculation is shorter than 24 inches. I extended that to 24 inches for the reason that we don't really know the exact location of the crack. The cracks could be here and there and there, and we don't know the actual location of the crack. So to make sure that you don't cut short of the development length, I extended it to the maximum 24 inches. I think it's safe and it's okay. The beam has the specification for the beam is for the concrete strength of 5,000 psi, and for the yielding stress of steel is 60,000 psi. The 125 kips is a factored load according to the ACI code, and the face of the cracks, both face, this side and that side, has a concrete friction of 1.4. The friction is depending on how the beam is constructed. This beam is constructed monolithically. It means the concrete is poured together at one time, so it has a coefficient of friction of 1.4. There are different frictions of cracks of concrete, and by the way, this is the Shear-Friction Method of analysis, and we're using that to design these reinforcement bars to prevent the beam from cracking, to prevent the beam from possible cracking. The formula for solving the area of steel, the reinforcement steel that we're going to be designing, is the AVF is equal to VU, the applied reaction that carried by the crack, times cosine 20 degrees plus TU sine 20 degrees. Okay, let me explain that VU and TU. The VU here is the adjacent side. When you're looking at this angle here of 20 degrees, the VU is a cosine. Cosine is adjacent over hypotenuse. The AC here is the crack, and the adjacent side of that is the cosine of 20 degrees. And the TU, when you look at this angle here, 20 degrees, the TU is the opposite side. So opposite over hypotenuse for the sine trigonometric function. That's why they have TU sine times sine 20 degrees. This is the resultant of these two forces here, the VU and the TU. The TU is a resisting force to prevent the reduction, the collapse of the volume of concrete, and also is the force preventing the concrete from slipping to wherever it is installed from the steel angle. It is the force preventing it from slipping out of like say if it's in the column, from the column, wherever it is supposed to be installed. So that's the TU, is the force. Is an opposing force to hold the beam in place to wherever it is to be installed. So the AVF is the area of this total area of the reinforcement, is equal to 125 the VU cosine 20 degrees plus TU sine 20 degrees divided by the reduction factor times 1.4, this is the formula here, times the Fy of 60,000 psi. Excuse me. The AVF now is equal to 100. Yeah, you work this out and it gives you 1.76 square inches. Okay, the area of this now is 1.76 inches square. And now that we have the area, the total area of the reinforcement bar, we have to try the size of the bar. Here I try bar number 6. Any bar number is divisible by 8 to get the diameter of the bar. So 6/8 is equal to 3/4, is 0.75 of an inch diameter of the bar. solving for the area of one bar, you have to solve the area for one bar of bar number 6. The bar number 6 is 3/4, it's 0.75 of an inch. So the area of one bar is equal to the pi d, diameter square, divided by 4, is equal to 0.44 inches square. The 6/8 here is a bar number 6. As I said, bar number is always divisible by 8 to get the diameters. This is the diameter. Okay, it's a pi d squared over 4. That's the area, and give us the area of 0.44 square of an inch. Okay, we got the area of one bar. Now to get the pieces of bar, number of bars altogether, is to divide the total area of the reinforcement bar divided by the area of one bar. that gives you the pieces of bar is equal to 1.76 inches square divided by 0.44 inches square. That gives you 4 pieces of number 6 bars. Since we use our calculation, we use number 6 bar. So there are 4 pieces of reinforcement that we're gonna be installing here at the length of development length up to 24 inches. So 4 of them is in there designed. Since we designed this based on the actual shear load, which is 125 kips, and because of the 125 kips applied to the steel angle, there is a horizontal force holding the beam horizontal and in place. The magnitude of the force TU is 20% of the VU. So therefore it is 125 times 0.2. This is 20% is equal to 25 kips. That's why we have 25 over here. Okay, so TU is 25 kips, and since we're using that the applied shear force, this shear force should be less than the applied shear force should be less than the design strength of the crack portion of the beam. The BN is the nominal strength of the crack surface, and according to the ECI code, not to exceed with the 2 criteria. Number 1 criteria is 0.2 FC prime times AC, and number 2 is 800 times AC. AC is the area of the crack. The beam is 16 inches wide, and you can see here the horizontal length of the crack is 4 inches. So the area of that is the AC is 16 times 4 divided by sine 20 degrees. It's a sine 20 degrees right there, right? This is the sine here, 20 degrees, and sine 20 degrees sine 20 degrees gives us 187 square inches. That's the area AC, and the applied shear force, the nominal applied shear force should be less than these two criteria here, the criteria 1 and criteria 2. So the total applied nominal shear carried by the crack portion of the beam, this is the applied load, 125 and the 25 kips. This is the applied shear load. So the applied shear load BNA is applied is equal to 125 cosine 20 degrees plus 25 sine 20 degrees is equal to 126 kips. That is the applied shear load on the surface of the crack portion of the beam. Okay, now the SI code has limitations for that. That the maximum strength of crack portion of the beam are as follows. The BN1 here is the criteria number 1. The design shear strength of the crack portion of the beam, criteria number 1 is equal to 0.2 times the concrete strength of 5,000 psi multiplied by the area of the crack is 187 square inches is equal to 187,000 pounds per square inch. To get the kips, you have to divide it by 1,000. That's why there's 1,000 here. Divided by 1,000, you get 187 kips. That is the criteria number 1. Okay, that is the strength, the design strength of the crack portion of the beam. Now criteria number 2 is 800 AC. VN2, criteria number 2 is equal to 800 times AC is equal to 800 times 187 square inches is equal to 150 kips. We have an equation here to be used. The BN is equal to BO cosine 20 degrees plus TU sine 20 degrees. That's number 1. Number 2 is the reduction factor, maximum design shear is 0.85 times the smallest of the BN1 and VN2. Okay, so that's the maximum shear stress in the crack portion of the beam. So we compare the steel 187 kips and 150 kips. We use the smaller value, which is 150 kips, to get the maximum design strength of the crack portion of the beam. So therefore the maximum nominal shear strength, design strength of the crack portion of the beam is therefore 0.85 times 150 is equal to 128 kips. Now according to the SI code, that the applied shear load should not exceed the criteria number 1 or number 2, the maximum strength design of the crack portion of the beam. So the maximum crack strength of the crack portion of the beam is 128 kips. So to check the answer if it's correct, to check if the beam is safe or not, based on the design of four number 6 reinforcement bars. To check that is to compare the 126 kips. Yeah, it is less than the design strength, which is 128 kips, so it is okay. So therefore the applied shear force, the VNA, is less than the ACI provisions, either 1 or 2. Therefore the design is satisfactory. Alright, so that's how you design the crack portion of the precast concrete beam, so that it is safe. The second scenario will be in the second video. That's another calculations, and this is the cross section of the precast concrete beam. Here are all the reinforcement. I'll explain this to the next video, and I think this is the end of the video, and thanks for watching, and don't forget to subscribe. Your subscription really makes a lot of difference to make my channel grow. Alright, thanks for watching. Bye.